We're going to, as I mentioned the other day, we're going to talk about chapter 8 here, which is gases. So we're going to do a little bit here this week, and we'll finish up the rest of it next week during discussion. Again, with the exam and spring break looming, don't want to get too far behind or too far off of your labs and stuff like that. So we will start here with gases and see where we get. All right, so let's talk a little bit about gases. Gases obviously are the state of matter where everybody has pretty much completely broke apart from one another. They are flying around in the container. Obviously, they are causing collisions. Those collisions, again, obviously is what we associate pressure with in terms of gases. So under sort of normal conditions, which is sort of room temperature type conditions of 1 atm. ATM is an atmosphere. It's a unit of pressure, and 25 degrees Celsius, which for all intents and purposes is usually what people sort of consider kind of like room conditions, the room normal temperature. Under those sort of normal conditions, we really don't find ionic compounds as gases, and that's because they are held together by really strong electrostatic attraction, the positive and negative attraction between those ions, as we talked about a little bit earlier today as well. It's a very almost as strong attractive force as you could get is between positive and negative guys. So under normal conditions, we really never really see ionic compounds in sort of the gas phase. To overcome that really strong attractive force, you would have to put in there an enormous amount of energy, and that just doesn't normally happen under normal conditions. In fact, you could heat, for example, that what I was talking about earlier, where you evaporate off the water and you're left with the sodium chloride, which is an ionic compound. You can continue to heat that thing with like a Bunsen burner, like really strongly and stuff like that. It will never really go into the gas phase. It will just really start to melt before it's able to do that. It's extremely high temperature to try to get it into like the gas phase. And under normal conditions, ionic compounds definitely are not usually in the gas phase. But covalent compounds or molecular compounds where we have sharing of electrons, those guys are a lot of times found in the gas phase. So things like carbon monoxide, carbon dioxide, that's hydrogen chloride gas, ammonia, which is a gas, and methane, which is the simplest organic guy you could have, the stuff that does come out to light your Bunsen burner there, are gases. Also, as we talked about when we were talking about elements and stuff like that, there's those guys that are diatomic guys, that are hydrogen, nitrogen, oxygen, fluorine, chlorine, that are gases as well under normal conditions. That's normally how they come. The major difference, though, between an ionic compound and sort of a molecular compound is that you can much easier convert a molecular compound into basically a gas than you can an ionic compound. So water is a very good example of that. Water basically here is held together by, as we were talking about a second ago, kind of hydrogen bonding. And when you heat something like water, this bond between the molecules, which is known as an intermolecular force, is a relatively weak force, and you can break that bond, and then obviously the water molecules can then go into basically the gas phase and make steam, basically, right, in the gas phase. So the general rule is the stronger the force that holds together like a molecule with another molecule, the less likely that you will find it as a gas under normal conditions. And obviously the weaker the sort of interaction between molecule and molecule, the more likely you would find it as a gas. And that's like something like methane, for example, as we were talking about earlier with oil. Methane is kind of similar to oil. It's a nonpolar sort of molecule. And the force that holds like a methane together with another methane is not an extremely strong force. So it doesn't take a lot to get it into the gas phase. And that's why we normally sort of see it as a gas under normal conditions. Now, substances that are found as gases, as I mentioned a second ago, we got our guys like hydrogen, nitrogen, oxygen, fluorine, and chlorine. Ozone, which is like in the ozone layer, is a gas, that's O3. And then obviously on our periodic table there, we have our noble gases in group 8. Those are what are referred to as being monoatomic. They basically come out as ones, so like helium, neon, argon, krypton, xenon, all the ons there in group 8 are monoatomic sort of gases. So here on the periodic table, everybody in purple normally will come as gases. Now, there's a good point to talk about a difference between two words that are sometimes used sort of interchangeably, but they really do represent sort of different things. A gas is really a substance that under normal conditions would be found in the gas phase. And a vapor is something that can be sort of turned into a gas, but under normal conditions are found basically as either a liquid or a solid. And the prime example of a vapor is what we were just talking about, which is water. Water under normal circumstances is found obviously in the liquid form, but it doesn't take a lot of effort to turn water into gas. You just basically need to heat it up, right? We do it when we like boil water, all the kind of steam that's coming out of it, that is basically water that has been converted into the gas phase. It doesn't take a lot of energy to do that. You just a little bit of a flame and get it to about 100 degrees Celsius, and it will break apart the bonds between the different water molecules, allowing them to go into the gas phase. That's also why we call it oftentimes water vapor versus water gas. Just kind of sounds funny, water gas. So water vapor, again, because it is normally found in the liquid phase. Any questions on that there? Now, one very important aspect of gases, as I mentioned, is pressure. And one very common way that we measure pressure is through the use of a barometer. Now, old school barometers used to be basically a pool of mercury for which a glass tube is usually inserted in it. And basically what happened is as atmospheric pressure basically comes down on the pool of mercury, the mercury will then rise in the glass tube. And that is typically how a barometer works. I believe in most cases they've taken these type of barometers out of schools because it contains mercury. I don't think you guys still have a mercury barometer in lab. I could be wrong. I haven't been up there in a while. But nowadays, for example, there's digital ones, alcohol-based sort of barometers and stuff like that. But a classic sort of barometer was made out of mercury and used mercury as sort of liquid. And there are really several different units of pressure that we often come about, but there's really three that we see a lot in this class. And one is an atmosphere, an ATM. One is a torr, named after the guy who invented the barometer there. And one is mmHg. MM is millimeters, and Hg is mercury. And that is because, as I mentioned a second ago, basically barometers were made out of mercury. And on the side of a barometer was a ruler, basically. And you could read the ruler a lot of times in inches. Mercury centimeters are millimeters. And that is where that name comes from, millimeters of mercury. The relationship is that a torr is equal to a millimeter of mercury. So they're basically the same number. You just change the units. It's a 1-to-1 relationship between them. And an important relationship is this one right here. 1 atmosphere is equal to 760 millimeters of mercury and 760 torr. So basically 760 is your magical number to go between those units. If you have atmospheres and you want millimeters of mercury or torr, you would multiply by 760. The atmospheres would cancel and you would be left with a torr or a millimeter of mercury, which is basically the same sort of thing. If you're starting with a torr or a millimeter of mercury, you would divide by 760. and that would leave you atmospheres when you divide by it in this particular case. There are clearly other units of pressure, but these are the three most common that we come across in this class and in most chemistry classes. But they're units like PSI, which are pounds per square inch. There's a unit of bar, which is a unit of pressure. I think we were talking about antifreeze earlier. If you ever look at your radiator cap, a lot of times it will say 1.1 bar or something like that on it. And that's a unit of pressure for to hold all your radiator and antifreeze under a certain pressure. Pascals, kilopascals are also common units of pressure. But for us, those are really the big three. It is atmospheres, it is torr, and it is millimeters of mercury are really the big three, with 760 being again that number to go, between the different units. Any questions on that there? So here's a much prettier picture of barometer. One interesting thing about mercury, as I think we might have talked about before, but mercury, if you ever use a mercury barometer or look at mercury, it actually has a meniscus that goes the opposite way, it goes upwards. And you would read actually from the top of the meniscus where it curves for mercury. Normal meniscus, right, goes this way. In the case of mercury, actually mercury is more attracted to itself than the glass container. So it comes in on itself and makes that kind of inverse meniscus, as opposed to a lot of substances like water, which are actually more attracted to the glass. So it rises up the sides of the glass, and that's what creates that sort of meniscus U that we're commonly see. All right, so we're going to talk about several different gas laws. And really all gas laws, for the most part, there's three sort of variables we deal with. Pressure, volume, and temperature are three sort of variables that we sort of look at. The first gas law is Boyle's Law. And in Boyle's Law, he looked at the relationship between pressure and volume, and he held temperature constant. And basically what was found through Boyle's Law was that a gas maintained at constant temperature is inversely proportional to the gas pressure. That's a lot of words that mean basically that when I have a small volume and I have my gas molecules in there, because it's a small volume, what's going to happen is those gas molecules have not a lot of room to fly around in. So because they don't have a lot of room to fly around in, there's going to be an increase in the collisions. It is actually the collisions as the gas molecules are flying around with the container and so forth that cause pressure. So because they're in a very small volume, a lot more collisions would see a rise in the pressure occurring. So as the volume goes down, we do see an increase in the pressure in this situation. And that is opposite of what would happen if we sort of increase the volume. By increasing the volume, what that means is these guys now have a lot more room to fly around. It's going to take a little bit longer for collisions to occur, and we will start to see collisions start to come down. The result of that is as the collisions come down, so does the pressure start to come down as well. So as the volume is increased, the pressure goes down. So basically, it's like, again, if we were all like in a very small closet all together, that's a lot of people in a very small area. The pressure is going to get very high in that closet. In this room, obviously, there's a lot of room. We could space out, not a big pressure sort of situation. And that is basically the relationship for Boyle's Law. And because of that, we can have what's in the box here, which is Boyle's Law. And you do need to sort of know this equation. And that is P1V1 equals P2V2. P1 and P2 are pressure. And in terms of units, they can be any unit you like, as long as they are the same unit on both sides. So everything properly cancels out. And V1 and V2 are volumes, which also can be the same volume on, it could be any unit of volume as long as they're the same on both sides. So no real restrictions here in terms of units, as long as they are all the same so that they properly cancel out. 1 and 2 is kind of like a before and after. So maybe you change the pressure and that will affect the volume, or you change the volume that will affect the pressure. It is really important to understand these relationships that occur here in something like Boyle's Law. It helps you with the math part of it to make sure, hopefully you maybe didn't make an error on that. So that's what we see here on the graph. If we take a graph of pressure versus volume, at smaller volume, we see a much larger pressure. And obviously, as the volume, it gives everybody a lot more room to move around, we start to see that the pressure starts to drop down. It is such a linear relationship, that inverse relationship, that essentially you could take any pressure times volume for a gas, different situations, and it'll actually equal the same number all the time when you multiply them together. So let's try one here. An inflated balloon has a volume of 0.55 liters at sea level at 1 atmosphere. It goes to 6.5 kilometers where the pressure is 0.4. What would be the final volume here of the balloon? So take a moment and see what you come up with. Look, so although we've only learned one sort of gas law so far, a very good approach when you're doing sort of gas law problems is, again, to sort of just pull out the information from the problem. So we do have a volume that is 0.55 liters. We have 1 atmosphere. So remember, atmosphere is a pressure. We have 6.5 kilometers, which is not really needed here, just useless information. We have another pressure that is 0.4 atmospheres. And we are looking for a volume here. So again, if you just sort of pull out the information, it should definitely kind of point you in the Boyle's Law direction. Since there's 2 pressures, 2 volumes, that would be a good one to sort of use. In this case, really, because we have 2 pressures, we want to make sure that our units here are the same, which they are. So that's good. If they weren't the same, then you need to do a conversion. It doesn't matter what unit you put it into, as long as they are both the same. We could call the first set of numbers the 1s and the second set 2s. That also doesn't really matter as long as you keep the values together that go together. Another important aspect of rearranging gas laws is whenever you move something across the equal sign, it ends up in the opposite location. So that's a quick way to figure it out. So although, again, they're not really written as fractions, you could think of those guys all as being up on top. In this case, we're actually looking for V2 by itself, which means we need to take the P2 to the other side, and it will end up on the opposite location on the bottom. Basically, we're dividing by P2 to the other side. That would give you P1, V1, P2 is equal to V2. And again, basically just dividing P2 to the other side, or put it in the opposite location. Any questions on that there? Now, the other important thing is to make sure you get obviously the right numbers in the right spots. So P1 here is 1 atmosphere up on top. V1 is 0.55 liters divided by 0.4 atmospheres. This is, again, why we want the units to be the same. Now the atmospheres on top and the bottom will cancel each other out. That will leave us just 1 unit left, which is liters up on top, which is good. And that is a unit of volume. So basically 0.55 divided by 0.4 going to get us a volume of 1.4 liters in this case. 2 sig figs off of everybody else, pretty much having 2 sig figs. Any questions on that calculation there? This is where understanding the relationship of Boyle's Law can be helpful, just to check, make sure the math was okay. What we know about Boyle's Law is as the volume increases, the pressure decreases, and as the volume decreases, the pressure increases. In this particular case, our pressure started at 1 atmosphere, and our pressure went to 0.4 atmospheres. That means that our pressure decreased which means what we should have saw with the volume is the volume should have increased, and it went from 0.55 to 1.4, so the volume did go up. So that's a good way to sort of check your math to make sure maybe you didn't mess something up or invert numbers. If you saw that the volume went down in this case, you definitely kind of messed up somewhere on the math part. So understanding the relationships can help you sort of roughly check to make sure you didn't maybe screw up the math really badly or anything like that. Any question on Boyle's law there? Okay. The next sort of relationship we're going to talk about is one that involves volume and temperature. And we're going to hold pressure constant. And this is what is known as Charles' law. And Charles' law basically showed that it is V1 over T1 is equal to V2 over T2. The volume units can be any unit you want, again, as long as they're the same on both sides, but the temperature here does need to be in Kelvin. Why does the temperature need to be in Kelvin? We actually see the reason why it needs to be in Kelvin here if we look at a graph of a bunch of different gases, of volume versus temperature. And if you take any gas you want and basically follow that line back to the temperature, every single gas ends up in the same location of temperature of minus 273.15 degrees Celsius. That number should look familiar. That is the number we use to convert really to Kelvin. And Kelvin understood that, and he called that basically absolute zero, because if we converted this to Kelvin, we would add 273.15, gives us 0 Kelvin, which is what is sometimes referred to as absolute zero, later renamed the Kelvin temperature scale. So basically, because of this and what he noted, every single time that you are dealing with a gas law problem and a gas law sort of calculation, and you have temperature, it 100% of the time needs to be in Kelvin. So you do have to convert it to Kelvin, which is the temperature in Celsius plus 273 gives you Kelvin. Even in problems where they give you the temperature in degrees Celsius and say, give me the answer in degrees Celsius, that is sometimes a confusing question, because people go, well, they gave it to me in Celsius and I'm supposed to give the answer in Celsius. So clearly I could leave it in Celsius, and clearly you should not. So you need to convert it to Kelvin, put it into the gas law, and then convert it afterwards and doing the gas law back to Celsius. So let's talk about the relationship here with Charles' law. So what ends up happening is, in order to keep constant pressure, the actual volume will adjust to do that. So let's talk about what would happen in this case if I increase the temperature. If I increase the temperature, will the gas molecules fly around slower or faster? They should fly around faster, right? They gain more energy, right? When you increase the temperature, gas molecules light a fire under somebody, right? They start moving a lot faster. So same idea here. So when we increase the temperature, the gas molecules would start to fly around faster. Now, if the volume did not move and they started to fly around faster, what we would see is the pressure should then start to go up, because they would be flying around faster. There'd be a lot more collisions. But under Charles' law, what we want to do is keep the pressure constant. So what ends up happening is the volume actually increases, gives everybody a lot more room to fly around in, even though they're moving faster. And what that's able to do is, because the volume adjusts, it's able to maintain the same number of collisions and the pressure remains the same. So what we see here in sort of Charles' law is, as the temperature increases, so does the volume. The volume gets larger, gives everybody more room to fly around, keeps the collisions constant, and that's how we're able to maintain it being constant pressure. The opposite is true. If we decrease the temperature, the gas molecules would start to fly around a lot slower. which means, and if we didn't do anything with the volume stayed the same and they're flying around slower, we would actually start to see a decrease in the pressure. It would start to drop. So what ends up happening when we lower the temperature is the volume actually goes down as well. And now what we have is these gas molecules in a much smaller area. They're able to maintain the same number of collisions, and thus the pressure remains constant. So in Charles' law application, what happens is the volume actually is the guy that adjusts to allow for the pressure to remain the same. The temperature increases, the volume gets larger. That way everybody has more room to fly around in. If the temperature is lowered, everybody's flying around slower, so the volume shrinks in on everybody, and that allows the collisions to basically, again, be maintained. Any questions on that relationship there? So since we talked about what would happen if the volume didn't move, there actually is a gas law that relates that, which is kind of similar to Charles' law, and that is, I'll put it here actually. Start right next to it. That is Guy-Lussac's law. Which is P1 over T1 is equal to P2 over T2. This is at constant volume. So in this situation, the volume actually is not going to move. It is locked into place. And because of that, what we see happen is what we would expect to happen. When we increase the temperature, everybody's going to be flying around a lot faster, a lot more collisions, and we definitely will now see the pressure start to increase because the volume is fixed. And vice versa, if we drop the temperature, we will actually start to see a drop in the pressure. In Guy-Lussac's law, again, because the volume is not adjusting in this case, it is fixed. So when we lower the temperature, we have less collisions, and less collisions lead to less pressure. So both of these laws are similar to each other. They both have basically a proportional relationship. Basically, as one goes up, the other goes up, and as one goes down, the other goes down. Any questions on any of those there? And obviously, same deal here. Temperature needs to be Kelvin. Yeah. So, like I said before, if it's a gas law and its temperature, it is definitely a safe bet to put it into Kelvin when you're doing the calculation. Any question on any of those there? All right, so let's try one here. In an experiment, 452 milliliters of a gas is used in a light bulb heated from 22 degrees Celsius to 187. What is the final volume? So take a couple of minutes, see what you come up with. Let's take a look. So, we have a few to choose from at this point. We got Boyle's Law, P1 V1 equals P2 V2. We got Charles' Law, V1 T1 equals V2 T2. We got Guy-Lussac's law, P1 T1 equals P2 T2. So again, if you're not sure which one to use, you just pull out the information. We got 452 milliliters, which is a volume. It is at 22 degrees Celsius, which is a temperature. It then goes to 187 degrees Celsius, and we are looking for a volume. So you could kind of see Charles' law there. You could also see, obviously, there's no pressure, so this guy's not going to help us. And obviously, there's no pressure, so this guy's not going to help us. So again, that's a good way to kind of figure out which gas law would probably apply. We could call our first guys here ones or second guys twos. There is something we do need to do with these guys right before we go into it, and that is obviously convert our temperature to Kelvin. We need to add a 273 there to each. That's 460 and 295 Kelvin. In this case, looking at Charles' law, V1 T1 is equal to V2 T2. In this case, we are looking to get V2 by itself. That means we need to move T2 to the other side. Again, the quick way to do that is it's on the bottom on the right, which means when you move it, it should go to the top there on the left. That would give us V1 T2 divided by T1 is equal to V2. Again, we're basically multiplying T2 to the other side. We want to also, again, make sure that we put in the correct number. So 452 milliliters, and that should be T2 up on top, which is 460 Kelvin divided by 295 Kelvin. In this case, the Kelvins cancel, leaves us with milliliters as our unit that is left. And that is a 452 times 460 divided by 295 yields us a 705, and the units are milliliters here. Any question on that calculation there? Again, we could kind of do our little check to make sure, our answer sort of makes sense. What we see in terms of the temperature here is the temperature went up, which means based on what we know, the volume in this case should also go up. And that is what we see. We started at 452 and we did go up to 705. So again, that does make sense based on Charles' law and sort of how things should move with one another. Questions on any part of that calculation there? Okay, so we do have several sort of gas laws here at this point. So as I mentioned, we have our Boyles Law, which is our P1 V1 equals P2 V2. That is at constant temperature. And again, as one goes up, the other goes down. We have our Charles Law, which is our V1 T1 equals V2 T2. This is at constant pressure. Temperature obviously needs to be in Kelvin. And again, as the temperature goes up, so does the volume. And as the temperature goes down, so does the volume. We also have our Guy-Lussac's, which is P1 T1 is equal to P2 T2. This is at constant volume. Also, again, here, temperature needs to be in Kelvin. And again, pressure going up when the temperature goes up and pressure going down when the temperature goes down. We can also add our 1 atmosphere is equal to 760 torr equals 760 millimeters of mercury. And I do have a space right there on the right, so why not add our other friend there, which is Avogadro. If you remember Avogadro, he had a number. Guess he wanted a gas law as well. So his gas law is V1 N1 is equal to V2 N2. When we think about Avogadro, right, it is 6.022 times 10 to the 23 equals 1 mole. So not surprisingly, moles are involved in his. N is the moles of gas. V is volume. And this is actually at constant temperature and pressure here. And basically the number of moles of a gas is proportional to the volume. So as one goes up, it kind of goes up proportionally to it. And obviously you would solve it like any of the other ones there. If you have 2 volumes in 1 mole or 2 moles in 1 volume, you would solve for any of those. Taking all these gas laws together and putting them together gives us really sort of the granddaddy of them all. Excuse me. And that is the ideal gas law. And the ideal gas law is PV equals nRT. Now, the ideal gas law is basically the gas law that we use for an ideal gas. One of the major things that makes something sort of an ideal gas is the idea that under normal conditions of pressures and temperatures, you can have a ton of gases all together in the same sort of container, and they basically will have no effect on one another. So having multiple different gases in the same container in an ideal situation, they pretty much do not interact with each other. So it's almost like having those gases in there by themselves. And PV equals nRT is basically built off of all the other equations that we just saw. It is different. All the other ones that we talked up to this point is like a before and after type of situation. Like, you got two pressures or two volumes or two temperatures. The ideal gas law is just basically one condition. So you got one pressure, one temperature, one volume. It is also the most restrictive in terms of units. If you are using the ideal gas law, PV equals nRT, the pressure 100% of the time has to be in atmospheres if you put it into there. The volume has to be in units of liters in order for this to work correctly. N is moles. And T needs to be in Kelvin. And really the reason why all those guys has to be in those units is because of R. R is the gas constant, which means it's a constant number. You always have it available to you. It is 0.08206, and it has units of liters times atmosphere divided by Kelvin times mole, which is why every single one of these guys need to be in those units for everything to properly cancel out. The good news is you probably will be given R, and it will have these units. So if you ever forget what units the gas, everybody in the ideal gas law needs to be in, is one of those units, depending on which one you are looking for. A lot of people will round this to 0.0821, which is fine as well. I personally use the top one because that is what they beat in my head and I cannot get it out. But a lot of people have now books will round it to 0.0821. So you can use either number in that case. Any questions on that? Yeah. For the gas constant for R? Yeah, that's exactly what the units are. Yeah. Other questions? Okay, so a couple of things about the ideal gas law, a couple of important things that kind of relate to it. First off, we'll start over here with STP. So STP stands for standard temperature and pressure. So when a problem or somebody tells you, hey, we're doing this at STP conditions, they're actually giving you two values. They're giving you a temperature value of 273 Kelvin, and they're giving you a pressure value of 1 atmosphere. So that is exactly what it means when something says STP. So sometimes people come across a problem and it says STP and they go like, they didn't give me any numbers. So when they do say STP, they assume that you know that the temperature value is 273 and the pressure is 1 atmosphere. Both of those things has to be at those numbers for it to be STP conditions. Now there is a special relationship, which is the top one here, and it's only at STP conditions. If you're at STP conditions, 1 mole of any gas will equal 22.414 liters. So this is sort of a conversion factor that you could use, again, only at STP conditions. That can allow you to bypass the ideal gas law and not have to stick the numbers into the ideal gas law. So if you are at STP conditions, you could use this to figure out moles or liters without using the ideal gas law. The good news is if you can't remember this conversion or not sure you should use this conversion, you should always then just use the ideal gas law. So you can use the ideal gas law for STP conditions. You just put in there 273 for the temperature and 1 atmosphere for the pressure. You can use the ideal gas law for any condition. So, that's your default. Go with it if you're not sure. But this one here is specific only for STP conditions. So if the temperature is not 273 and the pressure is not 1 atmosphere, you should not use that relationship. You should use the ideal gas law. And like I said before, if you're not sure, just go into the ideal gas law all the time and you'll be okay. And that's basically how we do get the gas constant. If we put into the ideal gas law and solve for R, which would be PV over NT. That would be 1 atmosphere, 22.414 liters, 1 mole, and 273. That is basically where we get the value for the gas constant of that 0.08206 number. The other thing about the gas constant is they don't always put it in the problem. So it is a value that you should know that you always have, and they won't, like in lights, go, hey, by the way, there R is this number. So they typically will not put it in a problem. It's just, again, assume that you kind of know you always have that number sort of available to you. Any questions on that there? Okay, so to finish up here, let's take a look at one here together. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas in a vessel that has a volume of 5.43 liters and a temperature of 69.5 degrees Celsius. Again, if you weren't sure what you should do, we obviously are looking for a pressure. We have 1.82 moles, which is N. We have a volume that is 5.43 liters, and we have a temperature that is 69.5 degrees Celsius. So if you just look at all the little letters there, you could maybe see the ideal gas law. But what you really don't see is you don't see 2 pressures, you don't see 2 volumes, you don't see 2 temperatures. So that eliminates pretty much all the other gas laws and only leaves you really with PV equals nRT as the only one that would work. Like I was mentioning a second ago, there's no mention of the gas constant here, right, in this problem. So again, you just need to know that you always have that value available to you. Now, we basically want to make sure everybody's in the correct unit. So since we are using the ideal gas law, the moles are in moles, so that's good. The volume's in liters, so that is good. The temperature, though, is in Celsius. So just like every other gas law, we got to convert that to Kelvin. So we want to add 273 to it. Gets you 342.5 Kelvin. And now we have everybody in the right units. So PV equals nRT. If we are looking to solve for pressure, again, not really written as a fraction, but basically everybody's on top. So my volume will end up in the opposite location on the bottom there. And that would give me that P is equal to nRT over V. And that's going to allow me to put in all my numbers here correctly. So the pressure here should equal my moles, which is 1.82. My gas constant, liters times atmosphere divided by Kelvin times mole. My temperature, which is 342.5 Kelvin. All that's going to be divided by the volume, which was 5.43 liters. Now, in terms of the units, the moles here and the moles here will cancel. The Kelvin here and the Kelvin there will cancel. The liters on the bottom and the liters on top will cancel. That leaves you just one unit standing at this point, which is atmospheres, and that is good because that is a pressure. So taking 1.82 times 0.08206 times 342.5 and hit equals, divided by 5.43 gives us an answer of 9.42 atmospheres, which would be our pressure in this case. Any question on any part of that there? So again, ideal gas law, basically a one set of conditions, but again, it is the most restrictive in the units. So that is definitely a very common mistake that people make. They kind of just throw it into the ideal gas law without changing the units. So you definitely want to watch the units when you're using the ideal gas law. Any questions on any of that there? Okay, we will stop there. Like I said,